This conference will now be recorded.
Excellent. All right, so welcome everybody to this special meeting of the E-VTOL Flight Test Council for electric aircraft and VTOL aircraft and aircraft that are making heavy use of novel electrical technology from a flight test perspective. I'm Peter Schmidt. I'm a member and chair of the Electric Flight Test Committee. And I want to start by thanking VFS and Jim Sherman for their sponsorship, along with the Society of Flight Test Engineers, and especially to Jim for running this meeting for us today and recording it. Today we have a special guest speaker, Mario Asselin, who has had a nearly 40-year career in aerospace, including stints as chief engineer, VP of engineering, and now engineering fellow at Bombardier. And Mario has graciously put together something of a framework for us to help us frame a discussion that started a few weeks ago at one of the council meetings. So what we're going to do is, Mario's got a lot of meat in this presentation, so we're going to go through it probably for the entire hour. We'll collect questions in the chat, and we'll try and make sure those all get addressed if we have time at the end, but definitely in a follow-up. So with that, I'm going to turn this over to Mario.
Thank you very much. So as I was saying earlier, the framework for this is not addressing one particular design. It's just a general approach to discussing energy reserve for mostly electric driven airplane. I did include the Zunum airplane here as a hybrid also, but it's not focused on any particular design. So what I intend to do is to try to provide some building blocks on how we can address energy reserves and what is a reserve from a given mission point of view. And this can serve as acceptable flight test practices to validate that reserve. It is not aimed at defining a regulatory value, right? So I'm not going to say you need something. This is just a building blocks on how we, based on the design of each one is handling, how do we get to an acceptable value for energy reserves, and we'll define what that could be. I say as a note that the references I'll be using are based on FAA. I could have picked EASA as well, but you pick one set of requirements, but it can easily be adapted to other agencies as required. Some of the references, so I'll quote a lot of the part 121.91 as examples for reserves. So the basic concept for energy reserves is that any aircraft shall be defined so that you can ensure a safe execution of a flight, including reaching a possible alternate, and to give time to the crew to satisfactorily complete the flight. So as a manufacturer, we'll have to define or provide a means for the operator to compute the required energy to complete that mission, accounting for variability en route and sufficient time margin to address variability. So the manufacturer shall provide a means to real-time monitor as well the energy state so that the pilot knows if he will make it there with the proper energy reserves. So energy reserves for electric airplanes should focus, so what I've tried to do, the reserve part of the energy should focus on the energy for the flight motors, what keeps you in the air, which is similar to the fuel reserve for power plant on traditional airplane. And that's a separate discussion from the energy required for emergency landing. The first one, the energy reserves, it's an OPS requirement. The second one, the emergency landing part, is a CERT requirement. With that in mind, we'll take a look at some of the OPS rules that define reserves. And we start with part 91, which is owner operators, for example. And it starts with no person may begin a flight. So right now we're saying that you should know if you can complete the flight go to the intended destination, right? Considering the winds and forecast weather. And there, from that point, that's under VFR, visual flight rules condition. From that point, once you get to your destination, assuming normal cruising speed during the day, you should have at least 30 minutes available energy. This is for an airplane. At night, need a bit more time to execute, need 45 minutes. On a rotorcraft helicopter, that time is reduced to 20 minutes, again, assuming normal cruising speed, which defines your energy use or your power required that you compute to define a reserve. The extra time, either 30 minutes, 45, or 20, is an energy consumption, right? A power consumption that is equivalent to a normal cruising speed. So it is not specified what that value is. It is left to the manufacturer to decide based on the design of the plane, altitude, speed, temperature, weight, what that value is. But it is an equivalent amount of energy for fuel, its fuel weight. If you are going with batteries, that will be energy per se. The extra time essentially for the airplane is based on the relative for the airplane. So I'm saying the 30 minutes compared to the 20 for an airplane wings is based on the fact that during normal flight, your power consumption is relatively low. And by the time you get to your landing place, you'll have to deploy flaps, possibly landing gear. Your energy use will increase. So they tend to put a bit more meat in that value because that 30 minutes is based on a normal cruising speed, drag configuration, power consumption. Whereas helicopters, you're using more power along the way, so they say at least 20 minutes. If I go to IFR, so right now I'm adding complexity, right? I go from 30 minutes. I know for IFR, no person may operate an airplane in IFR unless it carries enough fuel, considering weather and forecast weather. So again, ability to plan your energy consumption, to complete the flight to the first airport. If required, fly to an alternate airport. And after that, still have 45 minutes of normal cruising speed. And for helicopter, it's 30 minutes instead of 20. So the energy reserve is defined in terms of normal cruising speed. They say here, fly for an alternate airport if required. And there are requirements we will go through, for example, the part 121 that says it's required if you have such conditions. For 121 for commercial airplane, it starts again with no person may dispatch. So you cannot start the flight unless you have enough fuel to go to the airport you want to go to, so the destination. Thereafter, fly to and land at the most distant alternate. So go to a deviation if required. And thereafter, still have 45 minutes of normal cruising fuel consumption. And they say in some cases for VFR operation with special certificate holder, you could reduce that to 30 minutes. So it is a discussion of available energy based on a configuration cruise speed condition. The alternate is required for IFR if so no person may dispatch, again the word dispatch, unless it has one alternate, and that alternate is only required if within the predicted time of arrival, plus or minus an hour, the weather condition could be below minimum. If it's above minimum, you may not require that alternate. So you go back to, okay, so my flight in IFR, if I have acceptable weather at destination within plus or minus an hour, could be simply to dispatch to that airport and have 45 minutes once I get there under normal cruising fuel consumption. So we go on to electrical airplanes. Most all-electric airplane will initially have a limited range. That range can be from a few kilometers to several hundreds, but we are not yet, at least from what I can see, at the 1,000 kilometers or nautical mile range yet. So we may expect that the flight will be from a few minutes to less than 2 hours in duration. Under such condition, an operator should be able to have a good understanding of what the weather will be along the route all the way to the destination. So the focus then for operation of a all-electric airplane at this stage with the designs we have should be on the dispatch criteria. So again, you may not dispatch or you may not execute a flight unless you know you can get to the airport with known weather and have the proper reserve as defined earlier. So with that in mind, these are not yet fixed. I offer two scenarios. The first one I thought was interesting because a lot of the designs I've seen so far for electric are involve some of the vertical takeoff and landing modes. So it's okay for those airplane with a proper dispatch. So knowing that you can go from A to B along a route, if you have proper dispatch, knowing that the weather will be good enough for the flight all the way to point B within the time frame you have, 1 to 2 hours. A protected route would be, for the purpose of this discussion, one where the aircraft has multiple secure landing location along the way, including for VTOL airplanes, the possibility to land straight below this point. And you say essentially in this corridor, whatever that is, you can land anywhere if you are VTOL, for example. And that concept is similar to what I've seen, for example, when I go through a EASA ops rule for reduced contingency fuel, and they're a bit more lenient, which allows a decision point. So along the way, you have multiple decision points that defines how much fuel you should keep. It says that no alternate fuel is required if the decision point is less than 6 hours from the destination. Well, I know with our current designs, we won't have to fly that long, but the general approach is as you fly, you should have a clear understanding where is the closest point you can land, and in a protected zone, it could be right under. And that could define as an operational requirement some of the amount of reserve fuel you need. Then the reserve time is defined as the ability to address the weather and traffic variability. It may be a % of the flight. This is not time for energy for landing maneuvers. What I'm trying to say is I'm trying to remove the reserve, which is a normal operation, from the emergency, which is a requirement to be able to safely land the plane. And we'll go through some of the 1309 requirements a little bit later that says you cannot have a single failure for that can be catastrophic, right? So we say, okay, along the protected route, you should be able to land everywhere. Then we go back to, depending on your airplane, if you do need an airport, some of the electric airplanes will need an airport to land. You should have, along that protected route, enough airports to be able to land. And that's how you would plan some of your possible alternates or reserve fuel. Emergency power should allow sufficient time for so emergency power should allow sufficient time for emergency landing, and we make a distinction between reserve and emergency. I'll have a special slide a bit later on what emergency is. For a non-protected route, which is essentially Part 91 operation today, you want to dispatch from somewhere, go somewhere else, and along the way, could be a city, could be fields, whatever, it's not authorized landing sites unless you declare an emergency. So that's a non-protected route. And then you should have a proper reserve, and then a reserve energy cannot be based on emergency declaration. That I'm trying to make a distinction here in that if you get to a point where you have zero energy, you should be able to safely land somewhere. That's part of your emergency declaration. But above that zero, you should be normal operation. So the simplest approach for reserve becomes Part 91 definition. You get to your destination plus airtime under normal cruise condition. And then you look at all your design and you say, what is a normal cruise condition? It, just like all the operating rules, it is left to the manufacturer to define. It's an ops rule. It's not a CERT rule. The CERT rule should dictate the amounts of fuel-like energy, power plant, on board to safely land following the exhaustion of the normal energy. But the ops rule defines the amount you have to keep before you get to that exhaustion point. So as a note, I say that as you prepare, right, we'll have to address, and we'll have a slide on that, a fuel-like energy to do an emergency descent, which would be driven by CERT regulation. You should have a means as you prepare to validate your design to differentiate between your energy you assign for power plant compared to the energy you assign for emergencies. And I say it could be simply part of your basic battery design. You keep a %, or it could be a separate battery, right? The hardware separate that is tapped into once your normal energy is exhausted. And then I reiterate that the emergency power that you have should allow sufficient time to perform an emergency landing from the highest altitude above ground you expect following the exhaustion of the power plant energy. FAA, again, could be EASA, but FAA CERT will specify the energy needed for emergency. Now, that should be appropriate for the airplane intended use. What I'm saying here is, as an example, if you do design an airplane that's designed to fly for 2 minutes, it would be unreasonable to ask that you have 30 minutes of emergency energy on board. But if your airplane is designed to fly 10 hours, well, maybe 30 minutes is not too bad. So this is something that you would have to define. It is not necessarily 30 minutes based on the design of the plane and its intended use, right? And that should be every manufacturer having discussions with the authorities and saying, this is what this airplane can do. This is what is reasonable for handling emergencies for certification. Any questions so far? It's been very quiet. No? Okay.
I'm not seeing any questions in the chat yet, Mario, but I'll just reiterate. I think the important distinction you're making here is that emergency energy per the certification requirements is not the same thing as reserves mandated per particular operational requirements.
Correct. So we go back to battery management. Can I complete the mission? So we need to provide information to the crew. It's not yet standardized, right? I expect everybody will have a slightly different way to present the amount of energy available to complete a flight. But I believe that an indication that is similar to a fuel gauge, and I use the pipistrel example, the pipistrel electro, that is % or capacity in kilowatt hours, or a quantity that feels like a fuel, would be easiest for the pilot to adopt. But a quantity that is like this, right, just like jet fuel, energy level change with time is proportional to power use. So this indication is not an indication of flight time remaining. It is an indication of the energy that is available for the flight on the airplane. It should be, therefore, the change should be managed throughout the mission. So maybe an indication like this may not be enough, depends on your design, but may not be enough for the pilot to know if they can complete the mission. And maybe we need to go to the next step where we include a flight management system like that provides an indication of the capability to complete a planned mission. So then you would enter waypoints, expected burn, just like we do on larger planes, where you'll say, well, I intend to go from A to B through waypoint 1, 2, 3. I will be flying probably at a given altitude, speed, which will dictate approximately the amount of fuel I need, or energy in this case. Can I complete the mission with the proper reserves at the end? And that battery management system, the FMS, would have to account for the effects of things like battery discharge rate, expected temperature of the operating temperature of the battery aging. That indication, I'm suggesting, should be the effective battery capacity. So One of the things we know about lithium-ion battery is that as they age, they may not be able to provide as much energy as we have for a new battery. As well, if they operate cold versus warm, it may impact also the available energy for the flight. So that in some form should be part of your energy management system. And again, it goes back to, can I complete the mission and then have a operationally defined energy reserve. Then I need to find the zero. I've been dealing with electric airplane for a little bit more than a year now. I find it very interesting that we need to find the exact zero for that system. So one of the wording I'm suggesting, which I derived from 25.959, unusable fuel supply, rewritten in terms of battery energy. The unusable energy level for the flight battery, so what provides either lift, forward thrust, or so on, what allows you to fly under normal operation, flight batteries, must be established at not less than the quantity, energy quantity, at which the first evidence of motor malfunction or maximum power extraction not meeting a minimum defined. So you as the operator say, I need to be able, when I get at or just above zero, to still provide this much power to my propulsion system, lifting system, to complete a maneuver. And we do this on a big airplane by usually going with special modification to the airplane. We go to fuel starvation. So we find where that value is that would essentially shut down the engine. And that defines a zero. The batteries still have capability between this point, but we know that anything below that zero line is unusable for the purpose of mission planning. This is the zero that we need to have. From the zero, you define an ops reserve, a minimum, and I'm going to say 30, but it's not 30. It's how you would define it for your design, but an ops reserve that allows you to complete a mission from this level to this level and have sufficient time beyond that point. Now, after some discussion with some people, the zero level that I have here does not necessarily protect the batteries from damage. It simply guarantees a power extraction. And so I may have a point above that zero line where if I were to use that energy, it would impact the battery life. So I'd say below that point, maybe what's acceptable is that instead of saying I cannot use it, I can still use it, but this may require a maintenance action, an AMM, so airplane maintenance manual type maintenance activity. It could be replace the batteries, but it's okay as long as I get the proper power extraction from the batteries up to this point, which defines how I can execute a mission with some margin. The maintenance, possibly replacing the battery, becomes a commercial issue, not a certification issue. Testing, so on a larger plane with fuel, we modify the airplane and we test the airplane to engine starvation. So of course we do some adjustments, so we can actually only starve one engine out of two, for example. But we have to do this because fuel migrates in the wing and you have to make sure you feed the engine. Now, with batteries, the energy doesn't just migrate, it is there. So I suggest that this testing could actually be done on a test rig under proper condition that define what your battery capability is. But that greatly simplifies the testing, right? You can plan ground test on a rig with defined environment, defined power extraction until you have, and possibly do it multiple times, a reliable zero, compared to flying on an airplane where you try to do this at the minimum number of time because you're essentially starving an engine. Another thing they will have to do from a battery management point of view, life management. especially from what I've learned so far, battery and lithium ion, as you use them more and more, the effective capacity will reduce over time. Those batteries, even though you may charge them fully, may not have the available effective capacity to produce enough energy to complete a mission if you were to assume brand new batteries. So a full level would not provide the same level. An example again from Pipistrel, that's on there. It's on a display that's on the battery itself, so not necessarily in the cockpit for this one. Battery state of charge, what's available for the flight, and battery health. Each one of us will have a different design, and the manufacturers will need to provide a factored performance as the battery degrades. This is similar to engine degradation on conventional airplane, where fuel burn increases with engine age. But the impact on batteries is typically a larger value in terms of percent. The factor should probably be tracked in the BMS battery management system. And just like traditional engine, when you do performance monitoring, one should expect scatter. And I like this chart from GE that they presented back in 2006. This is an engine degradation over time. You can see scatter. And this is an engine where we improved the fuel burn by 1.3%. So you really have to squint to see the difference. Scatter is expected. So then we have our reserve, and we go to the part where we're going to talk about the emergency power. And then we go to a single failure cannot be catastrophic, right? So I list under AC 251309 or AC 231309, both the continued safe flight and landing. Beyond a point, for our case would be the exhaustion of the flight power. Continued safe flight and landing should be assured. So the capability to continued control flight and landing to a suitable airport. And then you go back to your mission design. If you're VTOL, maybe the suitable airport is right below you. Possibly using emergency procedure, but without requiring exceptional piloting skill and strength is required. And for this definition, some airplane damage may be associated with the failure condition during the flight or upon a landing. This is declaring an emergency. Catastrophic failure is a condition which prevents a continued safe flight. So from the point where you have flight power exhaustion, you should still be capable of continued safe flight and landing, which could be straight below. I've added the definitions for 1309 from part 23. A hazardous failure would be one that we could have a large reduction in safety margin, physical distress or higher workload for a crew, or even one injury in the occupant. So, whereas catastrophic would be simply unable to complete a safe return and landing. With that in mind, I start looking at emergency energy, the part that will probably have to be shown for certification. That energy should allow sufficient time for emergency landing from the highest altitude. Some airplanes conventional, will fly much higher, 20,000, 25,000 feet. Others will be a bit lower. On conventional plane, you might be able to glide all the way to land, but if you do, you still need to be able to control the plane, provide proper speed indication and altitude indication to the crew, and so on. You define what is required. On an airplane that has a wing and lifting rotor, do you allow glide to land? Can you do that? I mean, that you have to decide. But that energy that is required will have to be able to sustain you to a safe return to land condition. On an aircraft that has tilting wing and or rotors, you'll have to glide for a while, transition to an acceptable landing configuration and land. And on an aircraft that is mostly vertical lift, you'll have to be able to manage the descent rate, however you do it. But that's the emergency energy you'll have to keep in mind from the highest altitude you expect to be at, safely to a ground. And I say maybe some of the designs will include regen to slow the descent. but that should not be mandated. It's just you'll have to manage the descent rate to a safe landing. At this point, I'm going to talk about certification by analysis. Some of the material I have here has been extracted from a material I presented to the MFTC in front of FAA and Transport Canada, the MFTC being the Manufacturers Flight Test Council. These are Part 25 manufacturers. It was a presentation we made back in 2018, and it was to address Part 25 fly-by-wire airplanes, as most of us are moving towards fly-by-wire airplanes. But I found that some of it applies equally to the electrically powered airplanes that this council is looking at. And I've added this material after the 23rd of November meeting where Tom asked what assumption has been made to come up with the reservoir. How do I collect enough data to show that I am compliant? So the question to answer from my point of view is what do I need to validate? And when it's extract from the MFTC meeting, I put it as a note here. So what we said at the time, because we were transitioning from conventional airplane to fly-by-wire, subpart B testing defined by guidance materials supplemented by certification memos and issue papers. As we move towards fly-by-wire, FAA, in the case for this discussion, but Transport Canada and EASA keep adding additional requirements on top of the airplane compared to the conventional certification rule because fly-by-wire introduced new features. So you're still left with a defined scope of tests for cert with additional issue papers from Transport Canada, FAA, CREAS, EASA, and Transport Canada even has some certification memo, essentially allowing the use of other agency guidance material. But that becomes your cert testing to show compliance to the regulation. On top of this, you will do testing for development and investigation. So your scope of test is fairly large. So one of the questions is the regulation or guidance material still applicable? As we've been, the authorities are adding guidance to show compliance. They don't necessarily remove existing requirements that may, based on your design, not be applicable anymore. So it's always a question, can we not have something? Is there a better way to validate a requirement? So often the discussion gravitates towards guidance material on how to test, but those are based on a given design, and that may not be the best way to test another design. If a new requirement is added by issue paper to address a fly-by-wire, was another requirement dropped, and some requirements are not applicable anymore, but you have to capture that. And one of the questions we had for the authorities was, can I use company data for certification? The question always comes back of only if you have a good understanding of the configuration and it still meets the requirement, which leaves the onus to show that it is to the manufacturer, which is acceptable, but you have to have traceability all the way here. But one of the things I mentioned is that, you know, as Part 25 is very prescriptive, all our airplanes tend to essentially look the same. And the comments I had on this slide is this not limiting in terms of future airplane design? Which is always interesting as we try to move away from the conventional design. Based on regulation, it's often easier to come back to this, but it doesn't open the door to new ideas as much as it could, which Part 23 now seems to be able to do it. So one of the things I also mentioned to them that can flight tests be replaced by analysis? I expanded, I said analysis is used broadly here because analysis involves pilot in the loop simulator, rig testing, component level testing, and engineering data review simulation analysis. Really what I was trying to say here was that, do I really need to burn fuel to collect certification requirements? Maybe I don't. maybe there's a better way to do it. And I've put some examples here with Hearts, for example, has a ground rig for power plant testing and batteries. But you could also have your flight control system test on the rig with input, and then you can do fatigue testing on it. You don't necessarily have to fly. One of the things I said, between the Part 25 manufacturer, we have hundreds of thousands of hours of flight tests with data. And as we tend to build all these airplanes that are looking the same, we build a history of what we can do and what we expect the results to be. I said to the FTC, nothing beats data when it comes time to discuss and negotiate new approach technology with the authorities. As we explore, and the eVTOL world is a good example, everybody will have a slightly different approach to solving a problem. And that is okay. And if you bring data to the table and negotiate a way forward, it will be easier to do. And I like the example of AC 25-2, which was an AC that was issued in 1964, just before Part 25 became the law. At the time, propeller-driven airplanes were the norm, and jet-driven airplanes were sort of new feature. And the AC in 1964 said, upon the introduction of turbine-powered airplanes, the allowable range of takeoff and landing distance performance extrapolation was reduced. The reason for the reduction were that the turbine-powered airplanes had many new design features that were considerably different from those of previous type certificated airplane, which were piston props. Eventually, this guidance went away because guess what? The jet-driven airplanes became the norm. And I'm sure today, if we were to try to go back to piston prop airplanes for airliners, that we somehow forgot about that technology and we would reintroduce some restriction as we relearn. So I say from this point of view, we can then use this approach, knowing that what the eVTOL world is doing right now, but all electrical aircraft are doing, is something new. We bring data to the table and we elaborate based on what we know and what has been done before. FAA has recognized this AC 25.7 is the flight test guide for Part 25, but at revision D of the manual, they added some words on simulation, recognizing that the manufacturers have evolved and simulation has become a very important part of the approach. It starts by saying that it is difficult to establish guidance on using simulation instead of flight tests, which is totally understandable. All our design are unique. You can't really put that in the manual. But it says the following general principle can be used as guidance for finding what is acceptable. FAA starts by saying, in general, flight test demonstration are the preferred method to show compliance. And it's the same when I ask my pilot, well, what do you think about analysis? I said, I can't fly analysis, right? So flight test is the easiest way to accept. But when you do flight tests, you're only supposed to test the critical conditions. So you have to understand how you got there to pick what that condition is. So simulation may be acceptable when, for example, a flight demonstration would be too risky. You know, I'm talking about the demonstrating not only your zero energy level, but demonstrating you have enough energy available to complete a flight, so emergency power. Maybe that is best done by analysis, which could be a rig test. The required environmental or airplane conditions are too difficult to attain. I'm often asked for Part 25 airplane, well, you need to find the right crosswind with the right runway condition, could be wet and whatever. You can't physically, it's very hard to find all the combined conditions, and it may dictate the duration of your test, or even may not be possible to find the right combination. But I can collect enough information at various configuration and combine the information into a good simulation to understand what the impact is. The simulation used should be used to augment a reasonably broad flight test program. So you do collect a lot of information to validate all your components, and then you can test by simulation and then condition. And the simulation used to demonstrate repeatability. So that's the best way. Instead of keeping flying, knowing that the environmental condition will keep changing, maybe you can use simulation to validate the impact of the weight, the impact of the winds, and so on. It goes on to say for the AC, if it is agreed, so if you do plan to replace flight test by simulation, you should have a discussion with the authorities, right? If it is agreed, and usually with enough planning discussion, it becomes an agreed condition. The simulation should be of the type and fidelity that is appropriate for the task. So for example, if you need a pilot in the loop validation, you probably need a pilot in the loop simulator rather than purely a desktop. Should be suitably validated by flight test data for the condition of interest. And they do add, that does not mean that you need to test exactly the condition of interest. Again, it goes back to what type of risk do you have when you do the test. And it might be the build of multiple conditions to get the one that you want to achieve. And the simulation should be conducted in a manner appropriate for the case and condition. Again, pilot in the loop discussion. How to use big data. So for me, I decompose the maneuver into critical components that allow us to collect data from a flight test program that you understand you will do to start validating your model. And the example I had used for the MFTC is a tailwind landing, because a lot of discussion occurs for tailwinds of 15 knots on a large airplane where you have additional requirements. So I said I can break down the maneuver in terms of components that is flight path driven, which I understand is thrust minus drag over weight, which is an airplane dependent, your engine power, your flap setting, speed, altitude, pilot field of view, and collect that data. I can address sink rate, which will be different with tailwinds as a function of pilot reaction time. Flare requirements will increase. Do I have enough elevator power, more load factor, and so on. But I can do this away from a 15-knot tailwind conditions, which is very hard to get, and collect data. And then once that is validated by test, then I can present the data to the FA. And some of the questions I had during that meeting says, well, what about the tailwinds affecting your thrust? Well, that only happens when essentially near zero, which I can also collect by doing taxi tests. So again, I can revalidate the various components if I understand what the environment is going to do to create a suitable model that is flight test validated, not necessarily by flying that condition. So I go back to the questions we had. What assumption has been made? What do I need to validate? Well, we'll need to create a model that is just representative enough to be easily validated, but not so complicated that if it will fall apart if one variable deviates from target. So now you have to start looking at your design and deciding, what do I bring in that model that will allow me to complete, for example, a mission? Some of the notes I have from batteries, the discharge rate has an impact. The charge of the battery and the charging rate of the battery could impact the effective energy available. The battery operating temperature, either within the aircraft, or just the way the environment in which it's flying. The age of the battery, number of cycles or time, how many times you had deep discharge. And all this information should essentially be fed into a battery management system to provide cues to the crew on the effective capacity. And for each manufacturer, that battery model should be adapted to the battery design, of course, the mission profile of the aircraft, and from the AC, substantially validated by tests. So now, since we're going to be talking software, on my last slide, regression testing. I'm sure that you've had a chance to do some software, and how many times did we have the software right on the first try, right? So we go back. We will need to do regression testing. Every time we change something, regression testing is a verification that the software change does not affect existing feature. This is from the MFTC, and we were talking fly-by-wire. So for clause, control laws, a fly-by-wire system, it is a verification that the software change to address one part of the flight envelope that you had to tweak did not affect the rest of the flight envelope already tested. So a regression test is nothing but a full or partial selection of already executed test cases that you revalidate. And I just have a link here that shows a more detailed discussion. But you're going to look at your software, what you change, and revalidate that part plus a large enough envelope of that software to say, yep, it still does what its intended purpose was. And in our case for battery management, you're still able to predict a usable amount of energy. And that was for clause. You might have to do the same, but one of the questions we had was, do I need to refly a clause change? And so it goes back to what change. Select the level of regression analysis and select a limited condition. And the end discussion was, why do I need to burn fuel to validate a change? So in our case, why do I need to fly to validate a change if I can do most of it on a rig? So if you have a good model that is validated by test, that will help define your scope, and it will help control the scope in terms of planning, execution, and cost. A good model also allows the user to address failure cases, which is always a good discussion with the authorities. And with that in mind, that was the last slide. Any questions?
Excellent, Mauro. Thank you. We've had several questions in the chat, and I'm sure people have other ones, but let me jump to some of the ones in the chat here.
Okay.
So Tom asks, with respect to rig testing, what do we know about the effects of altitude on battery chemistry?
You don't. Well, again, it goes back to your proper design. Oh, is it packaged? Is it a sealed environment or not? And we don't want to dictate that, but you will have to define a model. So let we go back to a model that is just representative enough to define the discharge capability and the effective capacity of your battery. So you create a model. You could start with the assumption there's no altitude effect, but there's a temperature effect. And then as you go fly, you go repeat some maneuvers at low altitude and some maneuvers at high altitude. And you check your assumption, and if the model gives you what you expect. And the nice thing about electric airplanes, I'm sure you'll find a way to measure exactly the power use, right, as you fly from all your motors. And that defines a energy versus time. And then you can compare that to what your model for energy available within your battery is. And I know that lithium ions are very flat in terms of voltage versus capacity, and that will be an interesting challenge for a lot of us.
Okay, well, that actually takes us to another question from Chris, which is, how do we address energy display when the measure of the state of charge voltage varies with present discharge load? So, you talked about scatter in that fuel burn chart from the GE jet engine.
Yep.
And if we want the battery management system to provide information to the pilot so they can manage their power use,
yep.
Does that mean we're fated to have to work off some sort of worst case scatter number to make sure we don't go below our zero? Or what are your thoughts on that?
Well, again, if you use that state of charge as an equivalent fuel level, that is an energy available, and you have to validate that that value is okay. Now, can you complete your mission is a different discussion. And that energy level, which we had said, it's not an indication of flight time remaining. It's an indication of energy available, you'll need a flight management system that says, okay, you are here, you want to go to point B via this route. Based on this and the expected profile that you have along the way, you will make it or not. But it is just like fuel. I mean, if for Part 25 airplane, if I fly at 35,000 feet, I burn so much. If I fly at the same speed at sea level, I'll burn a lot more energy. So the fuel indication is not telling me much. My FMS or an equivalent system says, well, by the way, if you fly at sea level, you're not going to get to your destination.
Got it. Here's a question of clarification. Do you define the battery zero such that the emergency energy or power is above zero or below?
No, it's below. So zero is starvation. So just like a big airplane or even your car, you get to zero, the motor doesn't stop. It just says it may stop anytime after that. So it's unusable. Emergency could be extracted from this, but that zero, if this is a real zero, you know, batteries, that endpoint here may not provide power, right? It is, you still have a voltage out of it, but you may not be able to extract power. So if that's your zero, that's the one that guarantees you can do I'm going to use a conventional airplane, a go around. I will have so much power available to go around.
So your zero does provide, zero energy level leaves you the emergency power to proceed safely to a point of landing.
Well, that's for you to define. Again, when you do the emergency, okay, so let's say I have a conventional airplane with mechanical flight controls, right? Cables. If I have this, I could have zero power here, and I could have pneumatic, right? Let's go back very old, a pneumatic air altitude and airspeed indication. And the only thing I'm left with is a small light in the cockpit to actually read the display. That could be the emergency power if everything is mechanical. But if you are relying on rotors, maybe you need a bit more. An emergency, so pick your altitude, if 10,000 feet, you need to be able to control the plane to a safe landing as defined, and I'm going to use 1309, a safe landing, and get there, control the plane all the way there from that altitude to down, and you define what that scenario is. But this energy is the part that the FAA will ask to demonstrate in flight, which could be by analysis, right? So you could demonstrate, and I'm going to pick, it's electric. You could shut down the power to your motor and demonstrate this without actually having zero energy left.
Right.
And land, and throughout this, you could have, I'm going to say, a separate source of power and an emergency battery. It could be a quantity in your main battery, but let's say call it an emergency battery. You demonstrate the power use for landing.
That makes sense.
That part will have to be validated. That's it. I mean, by cert, you always have enough to do this, and it may mean, right? Let's say you start at 10,000 feet. It may mean that based on the expected effective capacity of that battery under your coldest condition, that may be twice the time, because under cold condition, you only have half the energy available to do the maneuver.
Okay, so we're almost out of time, but I wanted to give Hamdi Salam a chance to just, I know he has several questions, but Hamdi, go ahead.
Thank you very much. I wanted to thank Mario for this very interesting presentation, and also the eVTOL Flight Test Council for hosting this kind of discussions. I know we are very short on time. I will try to be as quick and summarize some points which I wanted to share with you. So also in EASA, we're having this discussion both on the ops side and on the airworthiness side. And most of the things we are hearing today are something which are already under discussion on our side. We started off with the energy, okay, and then we transitioned to the simulation. I almost got lost until then Mario started speaking about the BMS, and I understood where he was getting at. What we are trying to do here, at least my impression, we are trying to adapt a framework of fuel reserves of conventional aviation into electric propulsion, but we need to keep in mind that there is a big difference from what I've learned so far. So it is the relation between the amount of energy you're carrying on board and the performances of the aircraft. Unless very specific cases today, there were two separate domains. So until you hit that zero, which we are discussing, you almost knew that you could take all the maximum performance out of the storage system.
Yes.
With electrical energy, that's not the case, and this is going to drive a lot of discussions between the storage system and what you call the emergency landing or the continued safe flight and landing, if we consider urban air mobility kind of operations. Another thing I wanted to point out is that what you are addressing as energy reserve, we usually include it in the bigger scheme of the fuel scheme, being the final energy reserve only a part of this bigger scheme, because we are considering at the moment urban air mobility, kind of a commercial and transport operations, where you have more details of what you're actually doing before you hit those 20, 30, or 45 minutes. So we are including also other ways of defining, for example, the taxi energy, the trip energy, the destination energy, and all the other blocks which make up altogether your fuel scheme, okay, or energy scheme. And this brings us to your point about the indication. I am absolutely with you that we have to start thinking of something like the FMS. And the problem is that the FMS will not only provide us with what is the remaining indication, but it will also, for what we spoke in the beginning about this relationship between energy and performance, tell us actually if you can complete that segment of flight, because you may have the energy to get there, but it depends on what you actually need to do once you get there. Do you have to do a vertical landing, or is it a low power landing? So things could be quite different. And then two last small things. Sorry, I know I'm talking a lot. When you spoke about reduce contingency fuel, that's only for the reduction of one of these 8 blocks of the full complete energy scheme. So that's something you mentioned for.
Only affects this part. Yes.
Yeah.
Helps reserve.
And one last thing I wanted to share is the usable energy. So absolutely very correct comment about doing the comparison between the usable fuel, if we consider the fuel tank as a battery. But what I understood is that the difference is that it is not a fixed number. So the amount of error in determining your actual status of the battery, it depends of what is the expected load you're going to ask from it, also in the remainder of the flight. So
but that's what the ops rule do right now. It says under normal cruise condition, you should have 30 minutes, for example.
I'm speaking. Let's say, for example, you have a fuel tank of 100 liters. Today, we know that you have 97 liters of usable fuel. And that's because it has been established in the most conservative conditions with bank angles and whatever. So you know that until you have the 97 liters of fuel, you will not have a fuel starvation.
Yep.
What I'm saying is that if I have, and maybe I misunderstood because I am new to this electrical things. If you have a battery, okay, and you want to determine its energy it has in a given moment, the amount of error you have in determining the status on that moment is depending also on the amount of discharge or the profile you're going to discharge it in the future. So,
and that may be defined as a power used for, let's say, a go around or a transition power to land. Yes.
Yeah, but this is the point which I would like to highlight. It is not the amount of power. It is the error in knowing what is the amount of power. So the indication which should be given to the crew should take into account this variable amount of measurement error. It is not amount, it's because in the end the crew has to make its decision-making process on what is sees inside the cockpit, and we need to display to them what is the let's say most conservative error which we are reading the status of the battery in that moment.
I think that's what I said too. And we do the same for larger planes, even Part 23 planes. We find the zero in a conservative way, and we know that reaching that zero would be the first indication of an engine failure, for example. But above that, we're okay. And reaching that zero under normal cruising condition, nothing will happen.
Okay, so Mario, you are much more knowledgeable than me in electrical energy. I would like to ask you a question from an air crew point of view.
Okay.
So let's say, for example, I have an electrical multi-copter VTOL, and I have two different mission profiles. One mission profile is a normal mission profile where I want to take off and land after a cruise section. And another mission profile is I just want to hover for the entire amount of energy I have on board.
Okay.
What I understood is that when I begin the flight, if I'm doing the normal, let's say, cruising profile, the amount of error I have during takeoff is going to be much lower than the amount of error I have as soon as I lift off for the second kind of profile, because the amount of power I'm going to be using during the hover part is much higher than the cruise, and this kind of load profile is going to inject inside the system a much higher error. So my usable fuel or my usable energy would be much lower in the second case.
Your effective capacity will be less, yes, but I said the energy displayed is not a time indication. It's available energy, right? A helicopter that does hover will use a lot more energy than a helicopter that is in forward flight.
Gentlemen, I think this is Peter. I think the difference here may be around, do you present a worst case view to the pilot with no sort of additional information about the range of uncertainty, or do you provide an average with an uncertainty measurement to let the pilot make the decision? And probably this is driven by the fact that right now there can be such great variation on a battery that if you always presented the worst case, then we may not have enough energy.
Stay on the ground.
Yeah, well, exactly. I mean, I think this is an active topic. So I'm going to pause us here. There's been a lot of great questions in the chats. I'm going to collect those and make sure that we provide some responses for those on the VFS site. I'd like to thank Hamdi, who, for those of you who don't know, is a test pilot with EASA working actively on their special conditions for eVTOL. I want to thank Mario for presenting this terrific presentation. I think it's very useful for all of us looking at how we're going to actually go test fly electric aircraft. And enlightening with regards to the ongoing dialogue with our certification authority partners. So thank you everybody for attending today, and look for a follow-up email with links to the presentation and to the recording.
Thank you very much.